Welcome back to AI Paper Podcasts, your shortcut to staying right on the cutting edge of AI research.
It feels like every week there's something new, doesn't it?
Yeah.
Especially with large language models.
Absolutely. It's this relentless push for bigger, better, faster models, a real arms race, you could say.
And efficiency. That's often the secret weapon, the differentiator.
Exactly. Which brings us to today's paper. We're diving into a really interesting technical report from Huawei's Pangu team.
The Pangu Pro MoE paper. Mixture of grouped experts for efficient sparsity. I saw that one drop. Looks significant.
It really does. Okay, so for everyone tuning in, maybe just for the highlights, here's the quick rundown. Think of this as your 1-minute summary for the short form clips.
Go for it.
All right. The core idea is something they call mixture of grouped experts, or MoGE. It's a new way to build these models.
And the big problem it solves.
It tackles that notorious expert load imbalance you see in big. Mixture of expert models running across lots of hardware.
Right, where some chips are working flat out and others are just sitting there.
Exactly. MoGE is designed to ensure a perfectly balanced computational load.
Which means?
Dramatically better throughput. Huge for inference speed. And Huawei didn't just theorize, they built Pangu Pro MoE.
That's the 72 billion parameter one, right?
Yeah.
Optimized for their Ascend NPUs.
That's the one. Massive total parameters, but here's the kicker. It only activates 16 billion parameters per token.
Super efficient.
Yeah.
And the performance.
It actually outperforms bigger, dense models. We're talking 32 billion, even 72 billion parameter models, and leading open source MoEs on lots of benchmarks. State-of-the-art efficiency and capability.
Impressive. So that's the mission for this deep dive then.
Yep. We're going to unpack how MoGE actually works, look at that clever hardware-software co-design, and figure out what this all means for the future of AI that's both powerful and, well, efficient.
Sounds good. Let's get into it.
Okay, let's unpack that term we just used. Expert load imbalance. We mentioned it's a notorious problem, but for maybe some folks listening who aren't deep in MoE architectures daily, why is this such a critical thing? Especially when these models get huge.
It's fundamental, really.
Yeah.
So the whole appeal of mixture of experts models, MoE, is you get this massive parameter count, right? Tens, hundreds of billions, but you only actually use a small fraction of those parameters, the experts, for any given piece of input, like a word or token.
Right, so cheaper to run than a dense model of the same giant size.
That's the promise. But the challenge comes when you distribute this massive model across lots of different processing units, like Huawei uses their Ascend NPUs.
Okay.
What tends to happen in, let's call it conventional MoE, is that some specific experts just get picked way more often than others.
Ah, okay. So some experts are more popular, essentially.
You could say that. The standard routing mechanism, often called top K, looks at all the experts globally and says, okay, for this token, these K experts are the best fit.
Makes sense.
But crucially, that mechanism doesn't have any way to enforce that the chosen experts are spread out evenly across the different physical devices they live on.
Right. So you could end up picking, say, the top 2 experts, and they both happen to be on the same NPU chip.
Exactly. Or maybe one chip gets 3 experts to handle for a token, while another chip gets 0. That chip is just sitting idle.
And the one with 3 is working overtime.
Precisely. That creates what's often called the Straggler Problem. It's like, imagine a team project, right?
Yeah.
If one person insists on doing like 80% of the work for a particular task, everyone else has to wait for them to finish before the whole team can move on.
Okay, yeah. The slowest part dictates the overall speed.
That's it. So the device with the busiest experts becomes the bottleneck. It slows down the entire process, wastes computing resources, and increases latency. And this happens during both training and inference, which is critical for user experience.
So you have all this powerful hardware, but you can't actually use it effectively because the work isn't shared fairly.
Exactly. They even have a metric for it, the Imbalance Score, or IS. A higher score means a worse bottleneck. Some visualizations in the paper show this clearly conventional routing lights up experts clustered on just a few devices.
Okay, so that sets the stage perfectly. This straggler problem, this imbalance, is a major hurdle. So to tackle it, the Pangu team came up with mixture of grouped experts MoGE. You said it achieves perfect load balancing almost inherently. How?
It's genuinely elegant. The core idea is to enforce that balance right in the architecture itself. It's not an afterthought, it's baked in.
Okay, how do they do that?
First, they take all the experts in the model, let's say n experts total, and they deterministically divide them into a fixed number of distinct, non-overlapping groups. Let's call it M groups.
Deterministically, meaning it's a fixed predefined split.
Yes, exactly. And crucially, each of these M groups is typically mapped to its own dedicated computational device, like one Ascend NPU per group.
All right, so experts are pre-assigned to specific devices in these groups.
Correct. Now here's the clever part. For every input token, the MoG Routing Mechanism guarantees that a fixed number of experts get activated from each of the M groups.
From each group, not just globally picking the best ones.
Precisely.
Yeah.
So if you have, say, K experts to activate in total, and M groups, you activate K prime, which is K divided by M, experts from each group.
Okay.
In the Pangu Pro MoE model they build, they use a very common and effective setup where they activate exactly one expert from each group. So if they have 8 groups, they activate 8 experts total, one from each device's group.
So every device must activate one expert for every token. No device gets left out, and no device gets overloaded relative to the others.
You got it. That guarantees perfect inter-device load balance. The mechanism computes scores like normal MoE, but then instead of one big global top K selection,
it does a local selection within each group.
Exactly. Local top K prime selection inside each group, then it just combines those results. Visually, the paper shows this leads to activated experts being perfectly spread out. The imbalance score we mentioned, it's inherently 0 with MoE.
Wow. That seems almost simple, but obviously very powerful.
It is. Now, they do still use a kind of auxiliary loss function during training. MoGE guarantees balance between groups, but this extra loss helps ensure the workload within each group is also distributed nicely amongst the experts in that group. It's like fine-tuning the balance.
Okay, that makes sense. So MoGE is this fundamental architectural shift, but translating that elegant idea into a real high-performance model like Pangu Pro MoE, especially making it sing on Huawei's own Ascend NPUs. That's the next big step, right? That hardware-software co-design piece.
Absolutely. And this is where the meticulous engineering really comes to the forefront. Pangu Pro MoE, as we said, it's a beast, 72 billion total parameters.
So huge.
But the key, again, is efficiency. Only 16 billion of those are active for any given token. That's crucial.
So how did they tailor it for Ascend?
They employed this really interesting hierarchical co-design strategy. Think of it in stages. First, a sort of coarse-grained filter. They looked at the basic capabilities of their Ascend platforms, memory bandwidth, latency on a single server to define broad possible ranges for the model's parameters, like hidden size, number of layers, etc.
Okay, narrowing it down based on hardware limits.
Yep. Then, step 2, they brought in domain expertise. The researchers used their knowledge to shortlist the most promising model configurations within those ranges.
Makes sense. Human expertise guiding the search.
And then, the really sophisticated part, they used an operator-level simulator. This thing could evaluate candidate models by correlating all sorts of hardware parameters, TFLOPS, memory, how the chips talk to each other, and it could automatically search for the optimal parallelism strategy.
Wow, so simulating performance before even building or training?
Exactly. It allowed them to find the sweet spot, the best configuration of Pangu Pro MoE for Ascend hardware. The paper has charts showing how this simulation process guided them to the final setup.
And that final setup had, 64 experts total, activating 8.
That's right. 64 routed experts, divided into 8 groups, activating 1 from each group, totaling 8 active experts, which gets you to that 16 billion active parameters out of the 72 billion total.
And beyond just the model configuration, they optimize the actual inference process too.
Oh yeah, multifaceted optimization. At the system level, they used complex, hierarchical, and hybrid parallelism schemes, really co-designed with Ascend's specific interconnect fabric. Algorithmically, they use compression techniques like quantization to shrink the model's footprint.
We'll probably touch on quantization later.
Definitely. And right down at the kernel level, the very basic software routines they developed, custom, highly optimized versions for critical operations like attention, specifically for Ascend. It's optimization across the entire stack.
Okay, building a model like this, 72 billion parameters, even activating only 16 billion, that training process must have been absolutely monumental. Can you walk us through that from the raw data pre-training to getting it aligned for real-world tasks?
Monumental is the right word. It's an engineering marvel in itself. They split it into 2 main phases, pre-training and post-training alignment.
Let's start with pre-training. The data must have been immense.
Immense is an understatement. They trained on a corpus of 13 trillion tokens.
13 trillion.
13 trillion. High-quality tokens, too. It was incredibly diverse: web pages, books, codes, STEM materials, multilingual content, even specific industrial domain data, and critically synthetic data generated to boost reasoning.
Wow. how did they structure the training itself with that much data?
They used a really interesting three-phase approach, actually grounded in theories of cognitive development.
Oh, cool, like stages of learning.
Kind of. Phase 1 was the general phase on about 9.6 trillion tokens. This was about building broad knowledge, linguistic understanding, standard stuff, 4K sequence length.
Building the foundation.
Exactly. Phase 2 was the reasoning phase, using about 3 trillion tokens. Here, they significantly ramped up the proportion of complex data advanced STEM, coding problems, synthetic chain of thought examples. The goal was explicitly to improve reasoning skills. They also bumped the sequence length way up to 32K here.
Focusing on harder problems.
Right. And phase 3 was the annealing phase, using the last 0.4 trillion tokens. This was designed to bridge the gap to the post-training phase. They introduced instruction-style data and more how difficulties stem, using a curriculum approach starting easier and getting harder still at that 32K sequence length.
That's a very deliberate progression. Did they have a way to ensure the data quality was high? 13 trillion tokens is a lot to curate.
They did. They developed a novel evaluation system using other Pangu models, already fine-tuned, to act as judges. These models scored the data on things like cleanliness, fluency, educational value, richness, and categorized it into almost 200 different types.
Using AI to curate the data for AI training. Meta.
Pretty much. This allowed for really fine-grained control over the data mix in each phase. Of course, this was all done on clusters of those powerful Huawei Ascend 800T A2 NPUs, high compute, good energy efficiency.
Okay, that covers the massive pre-training effort, but just raw knowledge isn't enough. These models need alignment, right? How did they handle the post-training?
Exactly right. Post-training is crucial for making the model useful and safe. They started with supervised fine-tuning, SFT. Here, they carefully curated the fine-tuning data using a 3-to-1 ratio favoring reasoning tasks, math, code, logic over just general instruction following.
Really doubling down on that reasoning capability.
They really wanted to build in strong inductive biases for step-by-step problem solving. They did this SFT over 6 rounds, progressively optimizing, and they did something really innovative here called checkpoint merging.
Merging checkpoints, how does that work? Usually people merge different models.
Right. But here, they merged intermediate checkpoints from within a single SFT training run. They had this 2-layer strategy, merging within related groups of checkpoints, and then merging across those groups.
Huh. What's the benefit of that?
The idea is that different stages of the SFT run capture complementary knowledge. Merging them helps the final model become more robust, generalize better, and integrate insights learned at different points in the fine-tuning process.
Clever. Okay, so SFT, then checkpoint merging. What about reinforcement learning? RLHF is standard now.
Yep, they used RL2. The algorithm is called Group Relative Policy Optimization, or GRPO. And they had a neat trick called the Zero Advantage Mask.
Zero Advantage Mask, what does that do?
Okay, think about RL. The model tries things, gets rewards or penalties based on how well it did compared to what it expected the advantage. Sometimes the advantage is 0, meaning the outcome was exactly as expected, no real surprise, nothing much learned. This mask essentially tells the model, ignore those zero advantage samples during your update. Focus the learning effort only on the samples where there's a real signal, a meaningful difference between outcome and expectation. It drives policy updates only from the effective learning signals.
Makes the learning more efficient, focused on what matters.
Precisely. And the rewards themselves came from multiple sources, a multi-source reward system.
Okay, what kind of sources?
They had correctness rewards for tasks where you could verify the answer, like math and coding, using a mix of rule-based checkers and LLM-based verifiers. They had preference rewards for open-ended questions, where another capable LLM acted as a judge comparing different responses. And they had auxiliary rewards like format validators and penalties for just repeating itself.
A comprehensive feedback system.
Very. And they even used a curriculum approach here too, dynamically assessing the complexity of the RL task to feed the model a progressively challenging but manageable mix, ensuring it kept getting useful reward signals.
It's just layers upon layers of careful engineering and optimization. Which brings us back to the infrastructure. You mentioned the MoG architecture helps with load balance, but the paper dives into even more optimizations specifically for training and inference on Ascend. What were some highlights there?
Yeah, the co-design didn't stop at the model architecture. For training system optimizations, they refined communication patterns, like how expert parameters are exchanged, hierarchical EP all-to-all, and developed an adaptive mechanism to better overlap computation and communication during pipeline parallelism.
And the impact?
Pretty significant. They reported a 35% relative increase in model FLOP's utilization, MPU basically, how much of the hardware's potential compute power they were actually using effectively.
That's a big jump in efficiency.
It is. And as we mentioned, the MoGE architecture itself was a huge factor, cutting the computational load imbalance across devices by over 50% compared to what you'd expect with standard MoE. They also fine-tuned things at the lowest level, like adjusting matrix multiplication block sizes and cache strategies specifically for Ascend, getting another 5–10% boost just from those kernel optimizations.
Okay, so training got faster and more efficient. What about inference? That's critical for real-world deployment.
Right. For inference system optimizations, they went even further. They developed this sophisticated hierarchical and hybrid parallelism strategy, or H2P. It's a smart way to combine different types of parallelism, tensor parallelism, expert parallelism, etc., for different parts of the model.
So not a one-size-fits-all parallelism.
Exactly. For instance, the attention modules might use one combination to minimize communication across different servers, while the expert modules use another combination to balance memory use and latency. It's tailored. Their communication strategy during inference was also heavily optimized. They replaced some standard communication patterns like all reduce with more efficient ones like reduce scatter plus all gather that cut the amount of data being sent by half in some cases. They even rearranged the order of operations to reduce computational load associated with communication.
Shaving off overhead wherever possible.
Absolutely. And they focused intensely on communication compute overlap. They developed fused operations combining, say, a matrix multiplication directly with the communication step needed afterwards, so the hardware isn't sitting idle waiting for data. Think GMMRS, group mapmul plus reduce scatter, and AGMM, all gather plus mapmul, streamlining the whole flow.
Sounds incredibly intricate. What about compression, like quantization?
Critical for inference, they developed expert-aware quantization. Quantizing MoE models is tricky because you don't want the quantization process to accidentally change which expert gets selected for a token. Their method addresses this, suppressing outliers and activations and ensuring consistent expert routing, even at lower precision like 8-bit weights and activations, W8A8.
And the KV cache. That's always a big memory consumer in inference.
Yep. They tackled that too with KV cache quantization and sparsity, using a tool they called KV Tuner to optimize it for Ascend, further reducing the memory footprint and speeding things up.
And finally, you mentioned custom kernels earlier.
Yes, for the real bottlenecks. The MOL attention kernel targets the attention mechanism, which can eat up 50% of inference time. Their custom version uses smart data transfer strategies and scheduling designed specifically for Ascend's architecture, resulting in a massive 4.5x end-to-end attention speedup.
4.5 times faster. Wow.
Yeah, huge gain. And another one, Swift GMM, accelerates the grouped mapmul operation used in the MoE layers, which is another potential latency hog, especially with many users hitting the model at once. Their kernel uses clever caching and buffering to achieve up to 95% utilization of the hardware's matrix engines.
So pulling all those optimizations together, the architecture, the training, the inference strategies, it leads to tangible performance differences.
Definitely. In the pre-fill stage, processing the input dropped because MoG activates fewer parameters, like a 16B dense model. Pangu Pro MoE has much lower latency and higher input throughput compared to dense models. And in the decode stage, generating the response, it maintains low latency for single users and achieves significantly higher output throughput for many concurrent users, thanks to that minimized KV cache and communication overhead.
Okay, all these technical details, the architecture, the optimizations, it sounds incredibly impressive on paper. But the real question is, how does Pangu Pro MoE actually perform against other models out there? What did the benchmarks show? And did they learn anything interesting about MoGE itself by testing it?
Right, the proof is in the pudding, as they say. And yeah, the results were really compelling. They ran it through a whole battery of standard benchmarks, MMLU, drop for English understanding and reasoning, CEVAL, CMMLU for Chinese, and tough reasoning tasks like Human Eval for code, GSM-8K, and math for math problems.
A comprehensive evaluation.
Very. Looking at the pre-trained model results, Pangu Pro MoE hit state-of-the-art or near state-of-the-art performance on key English benchmarks and most of the Chinese ones. It showed particularly strong math reasoning on GSM-8K.
How did it compare to well-known open-source models?
It consistently showed advantages over prominent models like Quen 32B, GLM 4 32B, Gemma 27B, even Llama 4 Scout in many areas, despite its sparse activation activating only 16B parameters compared to their 27B or 32B.
Doing more with less, effectively? What about the Instruct model, the one fine-tuned for following instructions?
That one also performed exceptionally well, especially in English reasoning benchmarks like MMLU Pro and DROP, and held its own in Chinese evals. But the really striking part was its performance on logical reasoning, tough benchmarks like Math 500, MBPP plus RAT, even things like the Chinese Math Olympiad problems.
How did it do there?
It achieved results that were competitive with, or even better than, state-of-the-art models that activate 32 billion parameters or more. Again, Pangu Pro MoE is doing this, activating only 16 billion parameters. It really highlights the efficiency gains without compromising capability on hard tasks.
That efficiency point is key. What about the raw inference efficiency numbers on Ascend?
They're pretty staggering. On the Ascend 800i A2 platform, during that prefill stage, they clocked an average input throughput of over 4,800 tokens per second per card.
How does that compare?
It absolutely crushed the dense models, over 200% faster than a 72B dense model, and over 40% faster than a 32B dense model.
Wow. And the decode stage, generating output?
For high concurrency scenarios, they hit nearly 1,150 tokens per second per card and pushed that over 1,500 with speculative decoding techniques.
That's incredibly fast throughput.
It really is. They also showed excellent results on the more cost-effective Ascend 300i Duo platform, proving it's efficient across different hardware tiers. And the quantization held up well, near lossless accuracy at W888, and still acceptable performance even at W488.
So the performance and efficiency claims seem very well supported by the data. Did the experiments reveal anything deeper about how the MoGE architecture behaves internally? Like, do the experts really specialize?
Yeah, they did some fascinating analysis on that. They looked at domain specialization. They found that tokens related to specific topics, like coding versus general text, do get preferentially routed to certain experts.
So experts learn specific roles.
It appears so. And interestingly, this specialization actually gets stronger the deeper you go into the model's layers. Layer 47 shows much sharper specialization than Layer 0. And reasoning tasks tended to show more specialization than general language tasks.
Huh. Makes sense that complex reasoning might benefit from dedicated expert pathways.
It does suggest that. They also looked at expert co-activation. Basically, how often different experts get activated together for the same token. Because MoGE forces selection from different groups, you see blank areas in the co-activation matrix where experts from the same group can't be chosen together. But crucially, the co-activation between different groups was consistently low.
Meaning the groups are doing distinct work, low redundancy.
Exactly. It indicates the experts aren't just duplicating effort across groups. They also check the intragroup expert distribution, how tokens were spread among experts within the same group. Thanks to that auxiliary loss we mentioned, the distribution was nearly uniform, confirming good load balancing even inside each group.
And globally, compared to other MoE models.
That was maybe the most direct validation of MoE. They plotted the global expert distribution for Pangu Pro MoE against another leading MoE model, DeepSeek V2. The chart for Pangu Pro MoE shows remarkably even utilization. Each of the 8 activated experts handles roughly 12.5% of the tokens. DeepSeek V2, using conventional routing, showed a noticeable imbalance, with some experts getting far more traffic than others.
So visual proof that MoGE's design really delivers on that balanced load promise in practice.
Absolutely. It directly highlights MoGE's superior global load balancing.
Okay, this has been a really deep dive. So wrapping it all up, what's the big picture here? What's the main takeaway from this Pangu Pro MoE work?
I think Pangu Pro MoE, and really the mixture of grouped experts architecture powering it, represents a significant step forward. It's a clear, strong demonstration that by really thinking about hardware, software co-design, by building a sparse LLM architecture specifically to work well with the underlying hardware, in this case, Ascend NPUs, you can overcome fundamental challenges.
Like that expert load imbalance we started with.
Exactly. And solving that doesn't just lead to, better benchmark scores. It leads to genuinely superior performance in terms of throughput and latency, and perhaps more importantly, significantly better efficiency and cost effectiveness for actually deploying these massive models.
It really drives home that scaling isn't just about throwing more parameters or more compute at the problem. It's about scaling smarter, making the software and hardware work in harmony.
Couldn't have said it better myself. It's about intelligent design meeting powerful hardware.
Which leaves us, and you listening, with a final thought to chew on. We see AI hardware, like these Ascend NPUs, innovating at an incredible pace. How much further can these ideas of deep hardware-software co-design be pushed? Could we see entirely new forms of specialized AI architectures, maybe even more sophisticated ways of grouping expertise that completely redefine what's possible for efficient, truly scalable AI in the near future?
That's the exciting question, isn't it? What comes next?